All right. Good evening, everyone. Welcome to Vancouver Kimberlite Cluster Seminar. Thank you for tuning in virtually from all over the world right now. I would like to introduce myself. I am Catherine Landoni, a Master's of Science student at the University of British Columbia, studying under Kelly Russell, and I'm the VKC host for this year. I have here with me virtually Barbara Scott-Smith, who, as well as being a consultant, is also an adjunct professor at UBC, and she is the convener for the 2021 VKC series, while Maya Kopylova is on sabbatical. The VKC is a series of seminars for diamond geology and related topics, and our goal is ultimately to bring together academics and industry professionals. I want to acknowledge SRK Consulting for being a long-standing VKC sponsor. I know that we are pretty well versed with Zoom at this point, like a year later, but I just want to share a few housekeeping notes. Please keep your microphones and cameras off during the presentation because it helps the quality of the streaming. The presentation will be about 50 minutes long, and at that point, we'll transition to a questions and answer period, and I will be facilitating that. And then once we do about 15 or 20 minutes of questions and answers, we'll transition to a more informal social hour where I will stop the recording and then we can enjoy a beverage and a chat. So I am delighted to welcome Hayden Dalton, who is a PhD candidate from the University of Melbourne in Australia, where it's 11 a.m. Wednesday morning. Hayden is originally from New Zealand, and he completed his undergraduate and honors degrees in New Zealand at the University of Otago. His honors thesis was focused on the geochemistry of perovskite mantle xenoliths. He moved to the UK for two years, where he taught high school chemistry before returning to research through his PhD at Melbourne, where he is investigating several aspects of kimberlite magmatism in Finland, including their petrography, mineral and isotope geochemistry, as well as constraining the timing of emplacement. While nearing the completion of his PhD, he also works part-time as the coordinator of a STEM outreach program and as a manager of the Argon geochronology facility at the University of Melbourne. I'm told the scariest moment of his PhD so far was when he was mugged in Gaborone, Botswana after the 10th International Kimberlite Conference dinner. That's pretty scary. Outside of geology, Hayden is also an avid rugby and cricket fan, sports that may be foreign to many here in North America, where I am. Hayden's talk is going to be introduced by his supervisor, Professor David Phillips, who is head of the department in the School of Earth Sciences at the University of Melbourne. And he is also the director of the school's Noble Gas Laboratory. Welcome, Professor Phillips and Hayden. The floor is now yours. Professor Phillips.
Thanks, Catherine. And it's good to see so many of you at the talk today. And I guess thank you for inviting us to participate in this forum. I think it's a great forum for communicating about kimberlites and diamonds and these areas. As Catherine mentioned, I'm an argon geochronologist, and I've had a long, I guess, history with kimberlites. I worked for De Beers for 10 years before moving into academia. And one of my interests has been the timing of kimberlite magmatism. And of course, as most geochronologists will tell you, the technique that they're involved with is the best method for dating kimberlites or whatever other rock type they might be. And understanding the timing of kimberlite magmatism is really important for understanding the petrogenesis of the magmatism. And I often get questions from, I guess, researchers and folk in industry about kimberlite clusters. And, you know, kimberlites are not single eruptions, they're multiple eruptive systems. And you know, how long does it take a kimberlite to erupt? And adjacent kimberlites that appear to be fairly close in time, are they really close in time, and how close? And all the methods that we can apply, they all have pros and cons, and Hayden's going to talk about some of those. And I guess this was one of the few opportunities to try and determine and compare all the different geochronology methods that have been applied to kimberlites, or at least those most commonly applied to kimberlites. And as you will see from Hayden's talk, some give better precision, others might be a little bit more accurate and at different times. And so, you know, this topic, I guess, is really important for us to understand not only kimberlite petrogenesis, but also the history of fields in different parts of the world. And I know it's of great interest to folk in industry who always want to know how old their kimberlite is, or the lamproite, as the case may be. So, so I might leave it there and hand over to Hayden to carry on.
Great.
All right. My screen should be visible. So thanks for the introductions, Catherine and Dave. So as has been mentioned, my research is focused on kimberlite activity in Finland. And as part of my talk today, I'll be discussing some of the geological clocks that I've applied to work out when these kimberlites were emplaced. For those who are, I guess, unaware, although this is a pretty well-versed audience, I'm sure, kimberlites are derived from magmas. Often these magmas are emplaced in steep-sided cones, as we can see here. And because of their explosive nature, their fast ascent, there's often a large crater, which is we can see here in this artist's impression. I guess kimberlites are interesting to me for three key reasons. I'm just going to go through that very briefly now. First of those is that kimberlites are the primary economic host rock to diamonds. And here's an example of quite a lucrative find from a kimberlite, a diamond that sold for almost 70 million Australian dollars. Another reason I find kimberlites interesting is that they are the deepest derived magmas on Earth. We believe they come from depths of at least 200 kilometers beneath our feet, but potentially they come from as deep as the mantle transition zone, which is 600 kilometers or deeper. And this is based on evidence from diamonds. The third point about kimberlites is the fact that, because they're so deeply derived, they actually can transport pieces of the deep earth to the surface where we can hold them in our hands and study them. And we have some examples here of pieces of mantle perovskite that have been brought to the surface in kimberlites from Southern Africa. And just to labor these last 2 points a little bit more, kimberlites really are our primary way, our window into the deep mantle where we can physically sample it. Unlike movies such as The Core, we can't actually jump into a machine and we can't access the interior of the Earth physically. We can image it using geophysics, for example, but we can't actually hold pieces of a deep mantle in our hand unless we have these eruptions that tap these deep realms of the Earth. And just to put that into context, the deepest hole that humans have produced, I suppose, is 12 kilometers deep. And that's really only scratching the surface of the Earth's exterior, the crust. So kimberlites are important as our window into the deep realms of this planet. But despite their obvious scientific and even economic importance, if you consider diamonds, kimberlites still remain enigmatic. We don't yet fully understand the where, the when, the how, or the why of these rocks. And as Dave alluded to in his introduction, an important piece of this puzzle is working out when kimberlites have been emplaced throughout Earth's history. And in terms of working out this emplacement time or dating these rocks, there are three different decay systems or geochronometers that are commonly applied to kimberlites. The first is the uranium-lead system, and we use this system by analyzing grains of perovskite from kimberlites. There is the rubidium-strontium system used on mica from kimberlites, and also the potassium-argon or argon-argon system that is also used on mica grains from kimberlites. So my research has focused on kimberlite and related activity in Finland, of which there are a couple of key occurrences. There's the Kaivi-Kuopio field here on the margin of the Karelian craton, which is this red line here. And there is the Kuusamo cluster, where my mouse is, which is in the center of the craton. There is also a cluster of olivine lamproites on the border of Finland and Russia here. And I've also done some work on those rocks to work out when they were emplaced. So My approach in this part of my research has been to compare the argon-argon technique with the rubidium-strontium technique with the uranium-lead technique on the same kimberlites. And that culminated in this paper that came out at the end of last year, and I'll be presenting some of these findings to you all today. I'll begin first of all with the uranium-lead system. Now, as I mentioned briefly, this system is applied to the mineral perovskite, which is shown here in these images. And perovskite is a calcium titanium oxide mineral that has modest amounts of uranium and lead, but certainly enough for us to measure. One issue, though, with this mineral is something called common lead, and it's a common issue with this technique. Now, common lead, for those who might not know, is when we have lead incorporated into the mineral that isn't related to radioactive decay. So the mineral crystallizes and it has lead in its system and its mineral structure that isn't produced by the decay of uranium. And if we don't correct for this common lead, this non-radioactive or non-radiogenic lead, what we find is that our age is anomalously old. Now, to try and explain that a little bit diagrammatically, here I've got a Tierra-Wasserberg plot with this Concordia line here. And if we imagine the mineral zircon, now zircon is, I guess, what people would say is the ideal mineral for uranium lead dating because it doesn't have common lead. All of the lead in the structure should be produced by radioactive decay. And in most cases, in ideal cases at least, the zircon data will plot on this line, and then we can work out the age based on where it plots along this curve here. If we have common lead in our system, which is a perovskite issue, we start to move off that line, which means we have to do corrections to bring it back down. So this is one of the key issues we have to tackle when we're using perovskite to date a kimberlite. Now, because we often use a laser ablation system to date perovskites, we can't do what's called a 204 correction, because in a laser ablation system, we have a high mercury background, well, at least it's often the case that we have a high mercury background. And because of that having a mass 204, it interferes with the measurement of 204 lead. So we can't do that, which means we have to apply some alternatives. One of those alternatives is to plot our perovskite data uncorrected on a Tierra-Wasserberg diagram. And what that looks like is this, where we have all of these ellipses, these blue ellipses represent individual analyses of perovskite grains using a laser system. And then what we do is we put a regression line through that cluster of points, and that line goes back to this curve, and then we can read off the age. So we're relying on the intercept here to work out how old this sample is. And in this case, it's a relatively imprecise 530 plus or minus 70 million years. Now, the reason it's so imprecise is because if you look at detail at these points here, you could basically put a line almost anywhere through it. There isn't enough spread in the isochron space to accurately constrain where that line should go. And as a result, the error is much higher. So that's one option. Another option is to do what's called a 207 correction. Now, this is a little bit more complicated. And I guess the process here is that we use this regression line from our uncorrected data to then back correct individual points. Now, I'll just explain that using the diagram. So if you imagine we have our points here, we have this regression line. On this intercept here, we get a 207, 206 lead value. And what we do with that value is then we back correct every single point to work out a weighted mean age. Now, that might sound a little bit strange. I guess the outcome of that technique is that it produces very, very precise ages, plus or minus 2 million years now. But it might sound a little bit odd that we're using uncorrected data to form a regression to then go back and correct our data. And again, the criticism here is that this has been called mathematically circular. So I would say potentially not the ideal way to correct our data for this common lead issue that we face dating kimberlites with perovskite minerals. Another option, and probably maybe the most common, is to use what's called the Stacey-Kramer's evolution model. Now, this evolution model, how that works is that you put in an approximate age for your kimberlite, and then you, using the curve, you're able to obtain an approximation for the common lead value of your kimberlite at that time. Now, how this looks, again, this is the uncorrected data. So let's say this kimberlite was about 500 million years old. I would apply that age to the Stacey-Kramer's evolution model to work out what the 207-206 ratio should be for that time. And in this case, it's somewhere up here. And you can see that age has increased and precision is decreased, sorry, it's also increased, because what we're doing is we are now anchoring our regression on this y-axis. So instead of waving around through those points, we're now fixing it to this point, because that's what this value of 0.877 is what we read off the Stacey-Kramer's curve. But the key assumption here is we're saying that this Stacey-Kramer's evolution model actually accurately predicts or models the evolution of the kimberlite source through time. And potentially we can't be sure about that because Kramer's themselves, just 2 years after, they noted that the lead evolution of the kimberlite source was different to the evolution of the bulk Earth as they modeled it. So again, there's maybe some issues with that approach. What I did, and what I'm going to discuss with you today, is actually to analyze another mineral in the rock. So rather than potentially doing something mathematically or something with a model, I'm actually going to use the minerals in the rock to better increase the spread in the isochron. Now, the approach that we use is we take our grains in thin section or in a grain mount and of perovskite, and we hit them with a laser, and that laser ionizes individual atoms, and those atoms can then go through a mass spectrometer where we can obtain an age. And in some cases, the data can look pretty rubbish like this. So this is a pretty meaningless age, 280 plus or minus 300 million years, not very sensible. And that's because there isn't enough spread in isochron space. So again, because of that wiggle room where you can put the line through, we can't accurately constrain the age. So my suggestion, and I guess what I'm going to discuss today, is to actually utilize another mineral in the rock. In this case, it's spinel, shown here with these red circles. The reason for choosing spinel is that it obviously grows very closely in time and space with perovskite. So we can be confident that should faithfully record the uranium lead signature of the rock at the same time. The other good thing about spinel is that it doesn't have much or any uranium. So all of the lead that is present is common lead. And that's actually what we want in this situation. The downside though, is that we can't actually analyze spinel in situ. We don't have a standard for the laser to rapidly measure it. So instead we have to go through a bit of a painstaking process. We've got to crush our rock, and then in my case, separate a milligram or so of tiny 10, 20, 30 micron spinel grains. I've then got to put on a clean suit in the clean lab. I've then got to dissolve those grains using acid on a hot plate, and then also in an oven using a high pressure dissolution vessel. And then I've got to put them over these things called columns. Now these columns, they kind of act like a sieve. So everything that falls through the columns is stuff that we don't want. What we want to do is want to purify our liquid, our dissolved spinel, so we only have uranium and lead in our solution. And once we've done that sieving, or that column chemistry, we can then introduce that liquid, that solution, to the mass spectrometer, which has a plasma that's 10,000 degrees, or twice as hot as the sun. And that has the same effect as the laser. It basically ionizes the particles so that we can then measure them on a mass spectrometer. So what's the outcome of all of this work? This, I guess you could say it's quite laborious to this point, but what is the outcome? So remember, this was the age we got using only the in situ perovskite data. But then when we add the spinel data point here, we're actually extending the spread in the isochron space significantly so that our precision increases and the age now is much more realistic. And I can say that it is accurate compared to the other dating techniques, which I'll discuss later. If my painstaking mineral separation was perfect, this green point here for spinel should actually lie up here because there shouldn't really be any uranium. But what's in reality, it's very difficult to hand purify spinel from perovskite when they're so closely intergrown. So my value actually ended up being down here. But still, we have this great increase in precision and accuracy by analyzing another mineral in the rock rather than making any mathematical corrections or potentially using a different model. So what are the takeaway points for uranium lead? Well, there is a lack of spread using in situ data. In my case, at least, all I had was these clusters of blue ellipses, as we saw and it was very difficult to constrain where that regression line should go. And in every case where we tried it, if we include spinel, a co-magmatic phase, we increase both the accuracy and precision of the resultant age compared to just the in situ work alone. Now, we're arguing that we should use this co-magmatic phase in preference to that Stacey-Kramer's model because one of the things you need to know about your kimberlite to use that model is because you've got to know approximately when it was emplaced. So if you were exploring and you came across a new cluster of kimberlites and you had no idea how old they were, if they were Eocene or Cambrian or something like that, you couldn't actually accurately apply this evolution curve because it requires you knowing something about the rock. We also have to assume, using this model, that the bulk Earth evolution is the same as the lead evolution of the kimberlite source, which might not be correct. A final point, which I haven't touched on here in great detail, is the fact that if you're analyzing perovskite with a laser, you should use a perovskite standard. And Larry Hayden has characterized a standard for this work, and I would just encourage people, if they're doing laser ablation of perovskite, they should use that perovskite standard to match up with their own analyses. Okay, so that was uranium lead. Quick run through. The next technique I want to discuss is rubidium strontium dating of mica. And the question here, I guess, is should someone analyze phenocrysts of mica, or should they analyze the xenocrysts in the kimberlite or the macrocrysts? So for those who don't know, a phenocryst is a mica that has crystallized directly from the melt itself. So it's a primary phase. As the melt has cooled, the mica has crystallized from that melt. A xenocryst is a mineral, or in this case, a mica grain, that is foreign to that kimberlite. Because what happens as the kimberlite ascends to the surface, it plucks off pieces of the mantle and it incorporates them into that melt as it ascends. The key point here, though, is that these foreign grains, these mantle-derived macrocrysts or xenocrysts, they can still faithfully record the emplacement time because the kimberlites were emplaced in a very hot. When the kimberlites were emplaced, they're very hot. They're probably over 1,000 degrees, and the reset temperature for this isotopic clock is 400 degrees. So it means that, in theory, both these primary phases, these magmatic phenocrysts and these foreign xenocrysts or macrocrysts, should be able to be used to date a kimberlite. And that's something that I'm going to discuss and sort of validate in the next couple of slides. Before we get there, though, I just want to talk about some of the ways you can actually get an age from your phlogopite data. So it's commonplace for people to have a phlogopite data point and to regress that against some strontium values they might have for the kimberlite rock or minerals in that kimberlite. Another possibility is what's called a 2-point model age, where you have your phlogopite data point and you're anchoring it to an estimation of typical mantle values. This is very similar, probably the same actually, compared to using that Stacey-Kramer's evolution curve I discussed for uranium lead. The third approach, and I guess is what I'm going to discuss today, is using a single population of grains, but forming a 3-point isochron using an acid leaching technique. So let's say you've gone through crushing of your kimberlite and you've potentially painstakingly separated a whole bunch of grains, hundreds of grains potentially. What we do then, we separate our population of grains into 2, and then to one of those populations, we apply nitric acid. Now, the nitric acid is designed, or it could probably be hydrochloric acid too, potentially, that is designed to remove the calcite impurities that exist on the surface of mica grains and also potentially inside the layers of the mica. What we do is we keep the liquid. So once we apply the acid to wash off the calcite, we keep that liquid. And we end up with 3 fractions. We have a residue fraction, which is here on the left-hand side, and that is the mica grains that have been cleaned with the acid. We have the acid itself, which is called the leachate, and that contains the dissolved calcite. And then finally, we have our bulk fraction, which is the mica grains that have had no pre-treatment whatsoever, other than probably being washed in warm water, which is standard practice. So the result of that is a 3-point isochron based on these phenocrysts that gives us an age of 745 plus or minus 5 million years. So I would say it's a pretty good age, pretty precise. What about, though, if we compare this age to the macrocrysts, the xenocrystic grains that have come from the mantle but been incorporated into the kimberlite as it's ascended. So before I get to that, I just want to show you where these points plot. So this is the leachate point, this is the bulk point, and this is the residue point for the phenocrysts. Now, if we compare it to the macrocrystic age, we get an age of 743 plus or minus about 3 million years. So pretty great that both mica populations, completely different origins, can yield the same age within era for the kimberlite. A key point to raise here, though, is that the leachate for the macrocrysts plot here, but the bulk and the residue values, that they plot off the scale up here. And that's quite common in the case that when we use these mantle-derived grains, these foreign grains, we have a higher rubidium-strontium ratio, which means our isochron is much longer and our ages, as a result, are more precise. And there was a nice paper by Chiranjeev Sarkar out of Alberta, which actually talks about the importance of having higher rubidium-strontium ratio. So I encourage people to have a look at that if they want more information about those ratios. So what's the takeaway here? Well, the key point is that whether you analyze a phenocryst, so a mica from the melt, a primary phase, or we analyze a foreign phase, a macrocryst, we can still get the same age within era for the same kimberlite. So that's some validation. But in the interest of full disclosure, I do actually want to share with you a case where this didn't work, where this approach yielded an anomalous age. So these two yellow and black lines here, this is data for the Pipe 2 kimberlite in Finland. Now, this kimberlite I know from the other two techniques should be around 600 million years old, but that's not the case here. So one of the possibilities is that we have evidence based on major element chemistry that this kimberlite has had lots of crustal influence, crustal contamination. And it's possible that that crustal contamination has actually disturbed the rubidium-strontium system, or potentially even because of these granitic contaminants, I could have actually included some crustal-derived mica in my separates. So this is kind of one thing to be aware of. When you're separating hundreds of grains, just having a few foreign grains might throw out your age. And that's why the development of these in situ techniques that's happening around the world for rubidium-strontium is very promising, because it gives you spatial resolution. You can tell that what you're analyzing is actually going to be, you know, a magmatic grain or a mantle-derived grain, because if you wanted to, you could analyze it with a microprobe before to work out what sort of mica you're dealing with. And that spatial resolution is lost when we're using bulk separates. Just to speak about kimberlite specifically, there was a study out of Macquarie University here in Australia where they dated the monastery kimberlite, and they obtained an age of 90 plus or minus 4 million years, which compares really well with literature age of 90 million years too. So more work's being done on in situ work for rubidium-strontium, but I think the fact that we have spatial control over what we're analyzing, you could even analyze different zones of the same grain, is pretty exciting. So that's rubidium-strontium done now. The final technique I'd like to discuss is the argon-argon approach to dating kimberlites. Now, in my rocks, I had to use magmatic mica, and that's the case for any kimberlite. You should be using magmatic mica rather than that mantle-derived stuff I mentioned earlier. And the composition of my mica grains were kind of shit like phlogopite. They contain a range in barium and a range in potassium content. Now, for those of you who don't know how the argon-argon technique works, I'm just going to briefly run through that now. So on the right-hand side here, we have, let's pretend this is a mica grain, and inside that mica grain is atoms of potassium-39 and atoms of argon-40. Now, for the argon-argon technique to work, we need to convert these atoms of potassium-39 into atoms of argon-39, so we can work out the argon-argon ratio. To do that, we have to take our mica grains, wrap them up in aluminium foil, and we send them to a nuclear reactor. In this case, we use a nuclear reactor in Oregon in the US. And when they're in that reactor, our samples, are being bombarded with neutrons. Now that neutron bombardment, it converts 39 potassium into 39 argon. So now we have a mineral phase, a mica, that has both 39 argon and 40 argon, and we can work out the age. So this 40 argon I should have mentioned before is produced by the decay of potassium with time. One key point to raise here, though, is that when the samples are in the reactor, once they are finished being bombarded by neutrons, they're actually radioactive, which means it can be a month or two before the radioactivity is safe enough for us to handle them and then analyze them. So let's say we've got the samples back from the reactor, they're safe to use. We then put them through what's called step heating analysis. So here in Melbourne, we have an Argus mass spectrometer and attached to a laser, and that laser is an infrared laser. So basically what we're doing is we're essentially melting the grains incrementally. And as we heat the grains and they melt, the argon gas is released from the crystal lattice of those micrograins. I'll just show you what those steps look like now on some results. So, some results. Each of these boxes here, they represent one of those steps. So we're incrementally heating our grains and we're releasing gas at each step. What we're looking for typically is this plateau age where we have lots of incremental steps, all these boxes, where the age is the same or within error. And we can see here, this is a pretty flat release spectrum, and it did yield a plateau age. Now, these plateau ages are often considered, the gold standard. It's what we're actually looking for as argon-argon geochronologists. But is it always the true age, and are they always obtainable? Well, in short, they're not always obtainable. And one of the key issues here is that alteration is a problem. So the samples I'm flicking through now, these are grains of mica that had chlorite at their margins, and clearly that chlorite has disturbed the system enough with enough potassium loss that means that we get what I would say is a pretty rubbish release spectra, lots of humps. And again, here some more examples of altered grains. If we use more fresh mica grains from nicer kimberlite rocks, we start to get some nicer release spectra. Still not plateaus, but nicer in terms of them being more flat. In the cases where we do obtain plateau ages, we can see that they are super precise. So this is 764.6 plus or minus 0.9 million years. So it's a very precise age for a rock that old. Again, an example, 1190 plus or minus almost 2 million years. So these are what you'd expect to be great results, super precise plateau ages. One thing just to note here on these two examples, that there's a couple of steps. This one's got 1, 2, 3, before we get to this plateau age. Compare that to this example, which is kind of absolutely perfect, where we have completely flat release spectra across the analysis. So every time we heated that grain up incrementally, the amount of gas released, or the proportion of argon in that gas released was consistent across every step. And we have a nice age of 745 plus or minus 1 million years. So now what I want to do is kind of unpack this and kind of evaluate these plateau ages. We think of them as the gold standard, they're our target, but are they accurate compared to other ages? So on this plot, we have a series of stars, and these stars have error bars, which are often minuscule because of the precision of these plateau ages. And then if I now add a second type of argon-argon age, these triangles represent a total gas age. Now, these are useful when we don't get a plateau, which is not always possible, as we've seen. And what a total gas age is we aggregate all of the steps together in our experiment, and we weight those steps based on how much gas was released. So essentially, it's a bit like a weighted mean. So it's still a valid way to obtain an age from a kimberlite. We can't get that magical plateau number. A key point to note here, though, is that in almost every case, these triangles, these total gas ages, are quite a lot younger than our very precise plateau ages, apart from this one example where they overlap. Now, if we compare these two ages to our rubidium strontium ages, which are the crosses and pentagons that you can see now, we see the total gas ages and the rubidium strontium ages all overlap, but they're still, again, reminding you, younger than these stars, these plateau ages. Now, what if we add on the uranium lead perovskite ages? These are the squares. Again, we see the perovskite age, the rubidium strontium, and the argon-argon total gas age all overlap. But these plateau ages, these stars, again, they're older. There's only this one case in this green circle where we have a plateau age, a total gas age, a uranium lead perovskite age, and a rubidium strontium age that all agree. So the conclusion is that the plateau ages, these apparently the gold standard that we look for, is apparently older than the other ages with only that one exception. So why could that be? There are a couple of reasons why it could be the case. One of those reasons is something called extraneous argon, which can be excess argon, and that is when you have argon-40 incorporated into your rock by some other process other than radioactive decay, so other than the decay of potassium. Another possibility is inherited argon, where we have radiogenic argon that's included in your sample from some older process or some previous event. The other possibility is something called recoil. Now, if you remember, our samples go into a reactor and they are bombarded by neutrons for a matter of hours. Sometimes it can be 60 hours, sometimes it might be 5 or 6, but it's still, it's a long time firing neutrons at our sample. Now, what that can do is that can actually displace these atoms here. So if we imagine we're firing neutrons here, that can actually displace completely atoms of argon-39. They can be lost, ejected from the grain. The alternative is that they're redistributed within the grain, but they're redistributed to places that are weaker, so crystal defects, rather than being locked up nicely in the crystal lattice. Now, that's an issue because if your argon moves into areas that are weaker in your grain and you heat it up, then you're going to lose your gas or your argon from those weaknesses preferentially compared to the crystal lattice, which is not what we want. If we talk about extraneous argon first, we can kind of rule that out because our total gas ages, as I showed you before, they overlap with our other systems. So that means that our argon in the system isn't extraneous. Now, if we talk about the recoil issue, I'm going to talk through that a little bit detail now. So we have this more common case, I would say, where we have a few steps on our spectra before we get to this nice flat plateau, the thing we're aiming for. And then we have this one, I guess, potentially more rare case where we have completely flat release spectra. And in this release spectra, there is no evidence for recoil impacts. It's perfect. And as a result, all of our ages, our uranium lead, our rubidium strontium ages are consistent with that plateau age. In this, I guess, sub-ideal case, what's happening here is that we're losing argon-39 early in our experiment because it has been moved because of that neutron bombardment. We've gone from the crystal lattice to some weakness or defect in the grain, which means that we're losing 39 earlier than we would like. And as a result of that, these later steps that form the plateau, they have a higher ratio of 40 argon to 39 argon because our 39 argon is lost in those earlier steps. Now, in these cases, what we can do is we can use the total gas age to give us a better approximation of the true emplacement age. And that was shown by the previous plots where we saw the overlap between all the systems. So it seems that these age discrepancies are due to this recoil distribution effect. So this neutron bombardment smacking the argon-39 around. And this causes the preferential release of argon-39 relative to argon-40, and then we have that issue. So what's the outcome of this part of the work? Well, it's clear that the argon-argon technique can produce very accurate and very precise emplacement ages for kimberlites, but there are some caveats to be aware of. So when we have those younger steps before we get to our plateau, so we have that climbing staircase pattern before we get to that nice flat age, we should interpret those ages with a bit of caution. And where that discordance does exist, we can use the total gas age as a good approximation, as a reliable approximation of that emplacement age. And that's really important because we can't always get that perfect plateau, but the data we still obtain can be useful and meaningful. A key thing to consider is that grain selection is important. So you want to make sure that your grains aren't altered, there's no chlorite on their margins, and we need to use, where possible, nice, big, coarse phenocryst, because we understand that the bigger the phenocryst, the less likely it's impacted by that neutron bombardment, essentially more robust against that recoil effect. So that was a pretty whistle-stop tour through 3 of the most common dating techniques applied to kimberlite. So with all that in mind, the question remains, how do you date a kimberlite? Well, perhaps frustratingly, there is no right or wrong answer, I would say. I think all 3 techniques can still yield meaningful emplacement ages. Obviously, it depends on the material that you have, the analytical equipment you have, and also the mineral abundance. So how much perovskite do you have? How much mica do you have? Do you have macrocrystic mica? Do you have phenocrystic mica? All of those things will play into your approach. But let's say in an ideal case, my recommendations for how to approach this problem. If you're using the uranium lead technique with a laser ablation system, as we do here, then analyzing another mineral in the rock makes sense to me to extend the spread in the isochron and to improve both the accuracy and precision of the age, rather than perhaps using other common lead corrections that could be mathematically circular or rely on a crustal evolution curve that might not be an accurate picture, I suppose, of the kimberlite source. The other point is to use a perovskite standard for perovskite analyses. And what I would think would be great is if we could actually analyze these co-magmatic phases in situ. So rather than going through that painstaking process that I go through to analyze the spinel grains, if we had a standard for the laser, then in a matter of hours, we could analyze 50 to hundreds of perovskite grains and 50 to hundreds of spinel grains. So that's great. But what we need is a standard for that. So rubidium strontium now. Now, the key takeaway with the rubidium strontium system is that this method can be successfully applied to magmatic and macrocrystic mica. So whether the grains are from the melt or from the mantle, it doesn't matter. We can still obtain the same age using this acid leaching technique. Now, one thing that's really exciting in terms of developments is that we have this in situ technique coming on board where we can maintain spatial control. We can confirm that what we're analyzing is actually mantle derived or magmatic mica, rather than that issue that I faced with the crustal derived mica potentially. And as always, these in situ techniques, these laser ablation techniques, are much more rapid and much more cost effective. So the future is interesting in that regard. If we look now at argon-argon dating, a key thing here to consider is that this technique can produce very precise and accurate ages, but there are some caveats. Got to be careful with the grains that you choose. We can't always assume that plateau ages are the gold standard. And where we don't have plateaus, or maybe where we have plateaus that perhaps are a bit dubious, the total gas ages can provide an accurate approximation for the emplacement age of your rock. So if we don't have a plateau, we shouldn't discard the results. There's still some useful information to be had there. Okay, that's the dating side out of the way. Now I just want to quickly discuss the rocks themselves and kind of some ideas on what I'm working on in terms of their origins and evolution of kimberlite activity in Finland. Looking at the ages first off, so the Kaavi-Kuopio cluster I'll start with, which is the one here on the craton margin, before talking about the Kuusamo cluster's age, and then finally the age of these olivine lamproites. So the Kaavi-Kuopio kimberlites here were emplaced 585 to 620 million years ago. The Kuusamo kimberlites were emplaced between 730 to 750 million years ago, and the olivine lamproites and ultramafic lamprophyres were emplaced between 1180 and 1210 million years. The rest of the talk, though, I'm going to be focusing on the kimberlites rather than these lamproites, so apologies if you're listening to hear more about those. What we're looking at now is kind of what was happening in Earth's history at the time these kimberlites were emplaced. And here we have a tectonic reconstruction of some plates at this time. So we have, here's my area down here. This is Laurentia. And so what we have is a supercontinent. We have the continents amalgamated to form Rodinia. And as this animation unwinds, you'll see the plates start to move apart very slowly. So this is the very early stages of Rodinia breaking up. And then here, this blue dot, that represents the Kuusamo kimberlites that were in place between 730 and 750 million years ago. And just note their position on this red margin here. If we roll forward in time now, we see Rodinia breaking up completely. The Iapetus Ocean is opening here, and this is really the disintegration of Rodinia completing. But now we have the second group of blue dots that appeared, and that is the kimberlites from Caviquopio that were in place between 580 and 620 million years. So what may have promoted magmatism, we can't be sure, but some ideas. If we think about that red margin I mentioned before, what that red margin actually was the boundary of what we call a large, low shear wave velocity province, which are these regions of the deep earth that are thought to persist for long periods of geologic time. And they're thermally anomalous, and also they show up very strongly on geophysical imaging of the earth. And these provinces, these piles that exist at in the deep earth, what they actually, where they exist is at two different poles of the earth. There's one, the Pacific one, and the African one. And the key thing with these provinces is that they are thought to be the generation zone, potentially, of mantle plumes, which are hot upwellings from the mantle, from the deep mantle. And so one potential trigger for this kimberlite activity in Finland is the mantle plumes or the mantle upwellings that were responsible for the breakup of Rodinia. There must have been a trigger to cause those plates to move apart. And the mafic dike swarms that exist in this part of the world and the other kimberlite eruptions that exist in this part of the world at this time may possibly indicate that there is a role to play with mantle plumes here. So that's one possibility. Now, if we jump forward a little bit and look at the isotopes of these rocks. So this is a hafnium versus neodymium plot. And in the background here, I've got the global kimberlite database. And this darker red zone, that indicates the most common composition for kimberlites. This is the most densely populated part of the graph. And if we look at my Kusumo values, this is the older kimberlites, the 730 to 750 million year old kimberlites. We can see they plot basically smack bang in the middle of what we'd expect for a typical kimberlite worldwide. Then, if we add on the younger kimberlites, the Caviquopio kimberlites that are 580 to 620 million years, we see this pattern where they're, first of all, a big spread in data, but they're quite far away from this Kusumo cluster and this typical composition. And there's a spread from sort of +6 to almost -9 epsilon hafnium units, and that's quite a big spread. That's unusual. And so the takeaway from this point is that these two kimberlite clusters, despite their proximity, they have a distinct deep mantle source signature. It appears the mantle that sourced the two different clusters was different, or at least the signature gives that indication. So for the rest of the talk, in the next sort of 3 or 4 minutes, I'm just going to unpack that distinct signature and provide some reasons sort of why that could be the case. So one possibility is that we have this process of assimilation. Now, assimilation occurs when the kimberlite ascends to the surface of the earth, and as it ascends, it's grabbing pieces of the mantle and the crust from the wall rocks around it, and basically it chews it up. So it chews up the material and incorporates that material into the melt, and it can potentially influence the chemistry of the rock. Now, it's actually been shown that this process, mantle assimilation, can change the major element chemistry of a kimberlite. Now, it's important to mention we know this for the major elements. And this is shown using the relationship between olivine cores in kimberlites and olivine rims. Now, olivine cores, which you can see here, they are derived from the mantle. They are foreign. So they act as our proxy. They can tell us what sort of mantle the kimberlite has been chewing up, essentially, on its way to the surface. And the rims, which overgrow those olivine cores, these are actually derived from the from the melt itself. So I've got the cores that are foreign, and then we've got the rims that come from the melt. So those rims tell us a lot about the primitive melt composition as that kimberlite was in place. And it's been shown worldwide, potentially, that the primitive melt composition of the kimberlite has been influenced by this mantle assimilation process, by this chewing up of mantle lithologies as it ascends to the surface. And then I took this further into my local area and found the same. So within a single field, the primitive melt composition can vary based on what these kimberlites are chewing up or assimilating as they're ascending. What isn't clear is can this assimilation process actually change the isotopic composition of a kimberlite? We know it can change the major element chemistry, but not so sure about the isotopes. So what's interesting is that there was a correlation in my case between the hafnium isotope composition and the olivine cores. Now, remembering that the olivine cores, they're our proxy for what the kimberlite is assimilating, because we can't do it any other way, essentially. Interestingly, though, there was also a correlation between the hafnium isotopes on the x-axis and the rims of the rim magnesium number of olivine and the spinel magnesium number and spinel titanium content. Now, these other three regressions here, they represent the primitive melt. So we also see a correlation between the hafnium composition and the primitive melt composition of the kimberlite. Importantly, though, there is no correlation between the hafnium composition and monitors for crustal contamination. So the takeaway here from the slide is that mantle assimilation may explain the distinct hafnium signature of these younger kimberlites and may explain this displacement from typical signatures. But what about time? Is there any temporal trends? Interestingly enough, there is a correlation between time and hafnium composition of these kimberlites. The older kimberlites have a more primitive, positive hafnium composition, whereas the younger kimberlites have a more enriched, negative epsilon hafnium signature. What else is interesting? There's also a correlation between time and our proxy for assimilated material, which is the olivine cores. And then further still, there's also a relationship with time for our proxy for primitive melt composition. So all of these together are suggesting that the kimberlite source is becoming enriched with time, but also the assimilated material is becoming more iron rich with time, and so too is the primitive melt. And all of these things together suggest that potentially progressive enrichment of the kimberlite source itself, so not just assimilation, could also explain these distinct chemical signatures for these kimberlites, which displace it from the regular trend. If we just unpack the assimilation hypothesis first, what that requires is that the mantle that's being assimilated is becoming progressively enriched with time. And that enrichment has to be drastic enough to cause this big shift in hafnium isotope space in a short period of time. The other important thing to note here is that it seems that the mantle lithosphere beneath these kimberlites has actually experienced kimberlite metasomatism. So it's very unlikely that assimilating this material would actually cause the shift in isotope geochemistry that we need to explain this signature, this abnormal signature, I suppose you could say. Looking at the time hypothesis, what that requires is that the source in the deep mantle becomes enriched with time, which is counterintuitive, because if you're extracting melt from a source with time, you would expect depletion rather than enrichment. So what mechanism could cause this enrichment with time? So as we're getting younger, why are the kimberlites apparently coming from a more enriched source? Now, one option, if we think back to that theory that I raised about these having a bit of a plume influence in their source region, one possibility is that we have a plume on the margin of one of these provinces, and the older kimberlites, so the ones that have a more primitive positive hafnium signature, that plume did not sample much recycled material. But as we advance in time, it's possible that that plume, as it's advancing, or as time advances, it's sucking more recycled material into its source. So potentially this progressive incorporation of recycled crust into the source could account for the increasing enrichment of the source of these kimberlites. That's just one idea. Some alternatives could be due to the fact that actually the Baltic shear was physically moving on Earth's surface across this 35 million year period. And as a result of that, we could be sampling different parts of quite a variable mantle. And also there could have been changes in the thermal conditions of these upwellings across that period of time. So there's some theories I'm working on. There's plenty of modeling to be done to validate those. But yeah, thank you for listening, and I'll leave it there.
Thank you. All right, so now we're going to move on to the questions and answers part of the talk, where we will all ask Hayden some questions and have him chat about it. Feel free to turn your camera on if you're comfortable and unmute yourself. Otherwise, you can send me a question in the chat and I can read it out loud. So who wants to break the ice first here? That was a really great talk.
Well, if nobody's going to go, first of all, I have to say it was a really great talk.
Yeah.
That's way out of my wheelhouse. It was super interesting, very well explained. And thank you for all of that. My question is really simple. When you're doing the uranium lead on the perovskite, but you can't use the same technique for the spinel, is that simply, and I think you said something near the end, is that simply because you don't have proper standards for the spinels?
Yeah, I mean, you could do it and you could use a different mineral as a standard, but there are some issues there in terms of the standard that you used might not behave the same as the spinel. So if there was a laser ablation spinel standard, and then maybe there is, I'm not aware of it, that's the main thing that's holding us back, I would say.
Well, because
so
it sounds like,
yeah.
it sounds like if you could find a standard, that would make your life a lot easier. And that looks like
I think it might.
Powerful technique.
You just need to have a massive chunk of spinel that was homogeneous, and we can break it into chunks and share it around different labs. That's really what you need to create a standard. So yeah, I guess if anyone knows of one that I haven't found, I'll be interested to hear it.
Awesome, thanks. We have another question in the chat, and I'll just read it out loud so everyone can hear it. So Nikita asked, have you compared phlogopite leachate to whole rock rubidium strontium when anchoring an isochron with high rubidium strontium phlogopite? Awesome talk. Thanks, Hayden.
Yeah, great question, Nikita. And I did, so what I did is I compared to my ages with using the leachate to whole rock strontium data that had existed in literature before my study started. And thankfully the ages were quite similar, potentially like a few million years older. I also try using the model age technique, which is where you just make an assumption about the strontium content of the mantle at that time. And those ages ended up being 5 to 10 million years older. So in short, using the whole rock rubidium strontium did work. And I guess the next thing for me to try is actually anchoring it against perovskite-based initial strontium values, which have been shown to be more robust compared to whole rock because of the alteration that kimberlites are very susceptible to. But good question.
Yeah, I've got a question. It's Tom McCandless. On your uranium lead dates with your ellipses and then your spinel number on the plot, did you use did the spinel at the upper end of the plot control the age in any way, or was that just shown as sort of a sample quality result? So in other words, are you fitting the age to the ellipses, or is the spinel having a role in that age? Because I would think at that position on the XY plot, it would have quite an impact on the age, right?
That's right. Yeah, that's the exact purpose. So that regression line actually swung the whole way around to be sensible because it was relying on that spinel point, which is further up in XY space. That's right. And ideally, it would be further along, but I guess I was showing that to indicate the quality of the separation, but also, yeah, definitely the fact that that point then becomes crucial to the regression. Yep.
Okay, thanks.
If nobody else wants to go, I'll thanks for the talk, Dalton. I've read the earlier paper as well. Can I share my screen quickly?
I'm happy with that. Yeah, if Catherine can allow you to.
Yeah, I say go for it. You should be able to, Herman.
Okay. So if you guys can see an EPSL paper 2015, I'd just like to point out that Jennifer Pell said it's outside of her wheelhouse, but she's the second author on the best study of perovskites that exists, and it's published. The reason it's the best study is because we dated 45 of 71 kimberlites in one cluster. And we also measure their sort of epsilon strontium and epsilon neodymium values. And so I'd just like to share the, two diagrams out of this paper, because it touches on this point of enrichment with time within one kimberlite cluster, which is actually presented in figure, here it is, I think it's just there, one moment. Sorry, guys. Just have to
figure 6 has got the strontium and the neodymium data.
Yeah, that's the two combined. I want to get there in a moment. What I wanted to show are these figures. So there's the secular evolution with time of strontium initial ratios and basically epsilon neodymium. Now, in the paper, it was interpreted in a particular way, but both of these things are enriching with time in one kimberlite field over a period of about 15 million years. So the same issue that you identified in Finland with a lower set of populational data, or a less well-constrained spatial and temporal data set, is evident in these kimberlites. These are type 1, group 1 basaltic kimberlites like nobody else's business, and Jennifer Pell can talk to that herself. The point about this demonstration is when you combine these two isotope systems, you go to figure 7, then you end up with something that looks like that. I'm just going to see if I can make it a bit bigger. Whoops. Here we go. Essentially, you can see what can be interpreted as a mixing line, which starts at its oldest end at the most primitive bulk compositions, and then incorporates enriched material through time, where that time is about 15 million years. Now, there's been a long controversy about whether that enrichment trend is a result of contamination in the mantle lithosphere, the lithospheric mantle, or whether it represents something much deeper, as you have alluded to. So my question to you is, if you have a choice between those two end members, very deep mantle, as you said in your talk, or lithospheric mantle contamination, how would you interpret the data from Chudleak?
Well, I would have to look at the, I guess, the mantle lithologies and their own isotopic characteristics. But I guess from my own modeling, what I've found is that you have to assimilate, crazy volumes of mantle to cause the shift in hafnium isotopes that I've seen. I don't have the spread in strontium data that you're showing for Chudleak, but at least for my case, the modeling I've done with the lithospheric compositions that I have, it doesn't seem viable to assimilate that volume of mantle, the mantle volume required to cause the isotopic shift. I couldn't speak to Chudleak. I'm not sure of the compositions of the lithospheric material down there. If it has the right compositions, then potentially, but I'd have to look at that before I could speak to that point. Do you have any inklings, Herman, yourself? I'm curious to hear it.
No, it just strikes me that these arrays start basically bang on everywhere where you see group 1 kimberlite start, in the middle of this green glob. And the green field is an amalgamation of data from legacy studies where you've done 1 or 2 or 3 kimberlites out of a field. And nobody's ever done this type of study that we've done at Chudleak. It's the first time ever. And what do you know? We get the full range of the field of group 1 kimberlites from the middle to the edges simply by studying one kimberlite field. And I think that's telling us something. I think that whatever is happening with Chudleak is characteristic of whatever's happening elsewhere in the rest of the world.
Cool.
Can I just ask a quick question on this one before you move on? So you're showing here, Herman, quite a shift in neodymium. We didn't see that in Hayden's data. It was only hafnium.
Yep.
What does that mean? Any ideas between either yourself or Hayden?
Look, so the error on an individual neodymium analysis is smaller than those yellow symbols. What that means is that those arrays are incorporating neodymium variations larger than you can satisfy with your analytical precision. So those are real, number one. And number two, there have to be several distinct sources for neodymium isotopes to make up that whole array. It's not just one source.
I'll comment on.
Yeah, sure, go for it, Graham.
I'll comment on this. Have you finished, Herman? I don't want to cut you off.
No, that's all I can say. I'm not an isotope geochronologist.
Yeah, I think one way that you can rule out, say, enrichment, if you mean introducing for the hafnium anyway, you're talking about. I mean, it's very easy actually to decouple the neodymium from the hafnium. So I'm not too troubled that you see variation in hafnium and not neodymium. That's fairly easily done on a mineralogical basis. But I think you can rule out enrichment per se, where you introduce something and then you rely on that enrichment process to generate the isotopic compositions. Because if you look at Hayden's data, he's got 9 epsilon unit variation over 30 million years. And actually you guys have got 4 epsilon unit neodymium variation in 15 million years. You can do that by radioactive ingrowth fairly easily by just driving an extreme parent-daughter ratio, but it's way more difficult to do it by enrichment, because the only thing you're doing with enrichment, I mean, it sounds like you're adding something, but you're not with isotopic enrichment, because you're effectively freezing in the parent-daughter. You're lowering the parent-daughter ratio, so you're not adding any more radiogenic daughter products. So it's very difficult to produce large isotopic variations over short time scales with what we call enrichment, i.e. incompatible element-based enrichment, just because of the way the relative compatibilities of these parent-daughter isotopes. So I think it has to be a mixing process, and well, if I had to put my money on it, it would be a deep mixing process rather than a shallow mixing process, just because it's harder to find materials that have got those sorts of properties in depleted lithosphere unless you hit metasomites, but they don't seem to do it actually.
I guess it's Tom again. It's so from mixing models, Graham, we still, and Hayden, we're still looking at igneous mixing models. Is that correct? We're still looking at trying to make more partial melts, or are we actually at this point? I'm a retired isotope geochemist, so I'm a bit out of touch with the world right now. So I'm trying to catch up with it. But I just think that when we try to do mixing models with an igneous process, it's a bit hard to get what you want. But with a fluid process, it might be a bit easier to do that, because you liberate the incompatible elements more easily into a fluid.
Graham, I might just quickly just say that, yeah, I am still exploring models here to working out, what kind of fluid or what kind of material has the compositions or, has the characteristics required to cause this shift in this period of time. And at the moment, I don't have a solid answer. It's definitely still ongoing. So I'm really welcoming these discussions that we're having now. But yeah, as of right now, I haven't figured out, what kind of material down there, if we're saying it's deep mixing, and how much of it, for example, and over what timescales is required to combine with the source of these rocks to cause this change. Yeah.
Yeah, I'll come in here. Tom, that's a very good question. And Hayden, I will, go look up a paper where Graham Pearson was the analyst, which was the first time that they ever analyzed by isotopes the fluid inclusions that come out of diamonds. The first author is Ofra Klein-Ben-David. It's a very interesting paper if you want to look for sources that can explain mixing arrays like the one that's on the screen at the moment. And I will stop sharing it with that piece of advice.
I hope Hayden, you don't feel like the three of us are beating up on you, but I guess we got lots of questions, and I'm going to leave the isotopes for a minute and come back to the geology. And I liked your reassembly of the continents at the time of the events for the kimberlites. That's a great approach. And you showed the rifting events, but during that period of time on Earth-Thirsty, there was already subduction happening. That's well past the early Proterozoic. So did you consider, and you actually, I was waiting for my favorite word in any of these talks, which is subduction, which you almost said, you said recycled oceanic crust. That was pretty close. But when you reconstructed those continents, can you comment at all about where subduction zones were at the time of that assembly?
I probably couldn't. There was subduction zones prior to that. So the subduction occurring at like 1.2 billion years off the Baltic Shield, so nearby to Finland. What I haven't done yet is actually reevaluate those models based on a paper that came out this year, which looks at time zero to about 1,000 million years ago, new reconstructions. So I'm curious to apply, to rerun those models, but using some newer constraints on the placement of those plates. So for that time slice, for when those kimberlites were actually emplaced, I'm not aware of subduction occurring at the same time, but certainly prior to their emplacement, there was subduction in the area.
Okay. Yeah, there should be some kind of guesses for that kind of a thing, because the Earth loses heat and it generates crust, and it has to go down somewhere. So you have to have a mass balance. So subduction has to be happening. So there has to be some way. It might not be exactly where your kimberlites are, but it might be worth looking into a little bit.
Yeah, good point. Thanks, Tom.
Are there any other questions floating around out there?
I'm happy to be off the hook if that's the case.
Yeah. Okay. Well, before we sign off, I just have a comment announcement to make, I guess. This is our last VKC for the next 3 months while UBC is on their academic summer. And VKC will be returning again in September. Likely, Barbara and I will still be organizing it at that time. And if you'd like to be on the VKC mailing list, please send me an email with your email for me to add to the list. And I can send my email in the chat in a moment. And I will also be sharing a recording of this talk that's uploaded to YouTube within the next couple of days. And with that, I will stop the recording and we will be officially off the record.